Hello and welcome to this video on using the standard basis to find a standard matrix. So in this video we're going to see what the standard matrix of a linear transformation is, or a matrix transformation. Those are both the same thing. And how to use the standard basis of the domain of a transformation, a linear transformation, to find this standard matrix the way it's defined. And I'll go over several examples of that and be done with it. This should be a relatively short video by my standards. So here we go. Alright, so what is a standard matrix for a linear transformation, or of a linear transformation, or matrix transformation? So let's let T be a transformation from Rn to Rm. We're only going between Euclidean spaces here under standard operations. Let this transformation be a linear transformation, right? That means that it satisfies that additivity property and homogeneity property that have been mentioned in previous videos, if you've been following along, as I'm assuming you have. So vector addition is preserved by T under T, and scalar multiplication is also preserved under T. Then a matrix A, right? A matrix A called the standard matrix for this transformation T exists such that T of x equals A times x, meaning that the output, any output of the transformation, can be written as a matrix multiplied by the input vector. Right, so the input vector is not changing. This is x, this is x. Where the columns of this matrix, the columns of A, are formed by the image of each standard basis vector in the domain in Rn. Right. Now I have in a previous video showed you that if you have a linear transformation, you can very easily write the output as a matrix times the input vector, and it's very simple to do that in a linear transformation. But the purpose of this video is to show you how we can use the vectors from a basis for the domain to also create this same standard matrix. So let me show you what I mean by that. All right, so for the whole rest of the video, I only have a few examples. I had the following instructions. Use the standard basis, the standard basis vectors of the domain to find the standard matrix for this transformation. All right. Now I did this again in a previous video where here's my, it's a transformation from R2 to R3, right? So my inputs are vectors with 2 components, outputs are vectors with 3 components, and here's the rule. Input x1, x2, output 4x1 plus 6x2 for the first component, 2x1 minus 7x2 for the second, and negative 3x1 plus 5x2 for the third. And I showed you last time, again, if you've been watching, this is very easy. If you recognize this as a linear transformation just by staring at it, seeing all the terms, pardon me, have a single variable factor to the first power, right? Then I could very easily write this as I'll have a 3x2 matrix where down the first column I'm putting the coefficients of x1, so 4 in the first component, 2 in the second component, negative 3 in the third component, right, for x1. And then down the second column, the coefficients of the second variable x2 in the output, there's 6, negative 7, and 5. And then this matrix multiplied by the input vector x1, x2 will give me the exact same stuff as this guy up here, the way the output is described up top. All right, and this matrix, right, this 3x2 matrix here, this 4, 6, 2, negative 7, negative 3, 5, this would be called the standard matrix for T. All right, so very easy to create on your own. Very easy to, again, once you see, if you recognize that it's going to be a linear transformation or a matrix transformation, it is really that quick and simple. Just down each column of the matrix, you're putting the coefficients of the input variables in the correct order. Now, what we're going to do today, in this video, is create this matrix again. And what we're going to notice here is that these columns, 4, 2, -3, and this column, 6, -7, 5, are going to be the images of the standard basis vectors for the domain. And the reason we're doing this is because later on, in other videos and in future videos, we're going to be looking at transformations between two, different kinds of vector spaces, not just Euclidean space. And if it's a linear transformation, you should be able to write a standard matrix for it, or write it as some sort of matrix transformation, matrix product. And you can use a basis for the domain, right? And sometimes, again, the domain won't always be a Euclidean vector space. It might be some other vector space. You can use the basis for a domain to help you in finding this matrix that defines the transformation. So again, very simple right now. All right, it's very simple. We don't really need to do this right now, but it will be beneficial later on. All right. So what is the standard basis for the domain for R2? Well, hopefully you remember this, right? The standard basis for R2 was the set with these two vectors, right? And remember, the standard basis vectors for a Euclidean space, Rn, were just the columns of the n by n identity matrix, right? So the columns of the 2 by 2 identity matrix, first column 1, 0, and second column 0, 1, right? Every vector in R2 could be written as a linear combination of these two, and these are independent. So what I'm going to do now is, let's find the image of these, right? Find the image under this transformation. Find the images of these standard basis vectors under T. So that just means plug them in. All right, when I say find the image of this input vector, it means plug it in. What's the output? The output is the image. So what's T of the first standard basis vector? 1, 0. Plugging in 1 for x1, 0 for x2. See, I'm getting 4 times 1 plus 6 times 0 for the first component. All right, just popping them in here. 1 for x1, 0 for x2. 2 times 1 minus 7 times 0. -3 times 1 plus 5 times 0. And do you see what this is? That's just 4, 2, -3. And this image, okay, this image, which is the image of the first standard basis vector, this is going to be the first column of the standard matrix for T. As we are seeing, I mean, I know, again, I already wrote it, but see how it's the first column here of the standard matrix, right? 4, 2, -3 going down there. That's just the image of the first standard basis vector under this transformation T. All right, and let's find the image of the second standard basis vector, 0, 1. So hopefully you're seeing that T of 0, 1 is equal to, again, going back up here, replacing x1 with 0 and x2 with 1, you'd have 0 plus 6, and 0 minus 7, -7, and then 0 plus 5, 5. All right, and here is the second column of the standard matrix for this transformation. All right, and again, you can see that up here, right there, 6, -7, 5, the second column of the standard matrix for T. is just the image of the second standard basis vector from the domain. And that's it, right? Because those are the only standard basis vectors for R2. So the standard matrix, so standard matrix, and again I'm writing it again, I know, is equal to, first column 4, 2, negative 3, second column 6, negative 7, 5, negative 7, 5, and there we go. Same thing I wrote earlier. And then that means you could also write the transformation, t of x1, x2 here as this standard matrix multiplied by the input vector. All right, and you can test this out if you'd like. I'll check it out with one example, one particular input. So for example here, what's the value of t? What's the image? What's the image of the vector 3? Say 3, negative 4. Why not? All right, so you could go back to the original way the output was described, right, the original rule here, and replace every x1 with 3 and every x2 with negative 4. So that'd be 4 times 3 is 12, and then 6 times negative 4 is negative 24. Right, so 12 plus negative 24 is negative 12 for the first component. Then 2 times 3 is 6, and then negative 7 times negative 4 is 28. 6 plus 28 is 34 for the second component. And then negative 3 times 3 is negative 9. 5 times negative 4 is negative 20. Put those together as negative 29. Right? So I get that this vector is the image of the vector 3, negative 4. But you could also do this, right? Or use that matrix product, right? T of 3, negative 4 is going to be equivalent to our standard matrix, right? Which was that 4, 2, negative 3 first column, 6, negative 7, 5 second column, multiplied by the input vector 3, negative 4. And hopefully you're seeing that it's exactly the same as that vector there, right? The image of 3, negative 4 that I got earlier by plugging it into the original way the output looked. And let's double check, 4 times 3 plus 6 times negative 4, that's 12 minus 24 is negative 12, great. Then second row, first column, 6 plus 28, 34. And third row, first column, negative 9 plus negative 20, negative 29, it works out. Right? Check on that. Great, and you could do this with any input, right? Any input here, you take this standard matrix, right? Take this matrix here and multiply it by that input vector, you'll get the output that you desire. Great, all right. So I'm going to do the same thing for these next couple of examples, right? Again, it's not too terribly difficult to do this, find the standard matrix, especially when it's between a linear transformation between Euclidean spaces R2, R3, R4, etc. So let's just take a look at another one. All right. So here's another linear transformation. Again, you can check it's linear by showing the additivity property and homogeneity property if you want, but I'm just take my word for it here. It's linear. So I'm going for a transformation from R4 to R3. Here's a vector from R4, got 4 components, x, y, z, w. And the vector with 3 components is the output, x minus 2y plus w, 4y minus z, and y. All right, now, like I said, you can very easily, with these transformations between Euclidean spaces, set up a matrix here. It's going to be a 3 by 4, right, dimension of the codomain by the dimension of the domain. A 3 by 4 matrix where in each column you have the coefficients of x, coefficients of y, coefficients of z, and coefficients of w, right? Again, in the proper order, in the order that they come in down the input column. All right, but this time I'm going to do it with just the way we show with the standard basis, right? So the domain here is R4, right? And the standard basis for R4 is these, this dimension 4, so show these 4 vectors, the 4 columns of the 4x4 identity matrix, right? So the 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. There's the standard basis for the domain for R4. Now we're going to find the images of each of these. Right. So what's the value of t here at that first standard basis vector? 1, 0, 0, 0. And that's 1 for x, and then 0 for y, 0 for z, 0 for w. So 1 minus 0 plus 0. So 1, then 0 minus 0, and 0, so 0, 0. So there is the first column. Right, this is when I write the standard matrix later. Here's the first column of the standard matrix for this transformation T. Okay. Now for the second standard basis vector, that second column of the identity matrix, 2x2 identity, 4x4 identity matrix, sorry. So T of 0, 1, 0, 0. Again, this is 0 for x, 1 for y, 0 for z, 0 for w. So I'd have 0 minus 2 plus 0, so negative 2. Then 4 minus 0, 4. And then 1. All right, 0 for x, 1 for y, 0 for z, 0 for w. All right, and this will be the second column. Now I'm just going to write second column. Just know that I mean, of the standard matrix for T and all that. All right, the value of the transformation, the image of the third standard basis vector, the 0, 0, 1, 0. And so I'm replacing x with 0, y with 0, z with 1, and w with 0. All right, so the first one, x, y, and w are all 0, so that's 0. Z is 1, so this will be 0 minus 1, negative 1, and then 0 down here. Okay, so here's the third column of the standard matrix for T. Right? And then finally, right, there's only one more standard basis vector to pop in. Right, so what's the value of this transformation T at the last 0, 0, 0, 1, the last standard basis vector for R4. So this is I put in 0 for x, right, 0 for x, 0 for y, 0 for z, and 1 for w. Well, 1 for w, 0 for everything else, so the first one's 1. Then there's no w's in this, no w's in this. Okay, so there's the last column, the fourth column of the standard matrix for T. All right, so looking at all 4 of these now. All right, so the standard matrix for this transformation T is, like I said earlier, it's going to be a 3, there's 4 columns and each one has 3 components. It's going to be 3 by 4. First column, 1, 0, 0. Second column, negative 2, 4, 1. Third column, 0, negative 1, 0. Fourth column, 1, 0, 0. And there we go. All right. And then we could go back and also write a different way to find the outputs, right? So we could also write that T of x, y, z, w here is equal to this standard matrix multiplied by the input vector x, y, z, w. and you can double check, is this actually equal to this up here? And it should be. It will be if I did everything correctly. And just as I did with the first example, do you notice how, I mean, I didn't have to do this, again, with between Euclidean spaces is very simple. From R4 to R3 here, those are Euclidean vector spaces. All you're doing when you set up the standard matrix is, just put the coefficients of these variables in the order of the columns. See how the first column here is just the coefficients of x. There's 1x, then no x, then no x, right? Second column with the negative 2, 4, 1, those are just the coefficients of y, negative 2y, 4y, 1y, right? Third column is just the coefficients of z, 0z, negative 1z, and 0z. And then the fourth column is just the coefficients of w, 1w, no w, no w, right? And then you have your input vector. Okay, so you could also now find outputs this way, if you wished, right? So if I said, what's the image of 1, 2, 3, 4, the vector 1, 2, 3, 4, you just take this matrix times 1, 2, 3, 4, right? And get a 3 by 1 column vector, a sum vector from R3. Or you plug in 1 for x, 2 for y, 3 for z, 4 for w up here. Same thing. You'll get the same result no matter what you do. Wonderful. All right, so I got one last one. Again, you see how simple this is, I'm hoping, to set up a standard matrix for a linear transformation, a matrix transformation. All right, so this one, T is from, it's an operator because my domain and codomain are the same, right? So it's a linear operator, a linear transformation. Such that I used A and B for my components instead of x1, x2. So the value of t at AB, the image of AB is negative. So the first component in the output is the opposite of the second component of the input, and the second component of the output is the same as the first component of the input. All right. So again, standard basis. Now I'm just going to find the images of the standard basis vectors. Right? Images from R2, right? Standard basis. Now I know the domain and codomain are the same here, but when you're talking about finding the standard matrix of a transformation, you're plugging in the standard basis vectors of the domain. So images of the standard basis vectors. And I've already put this one up. I'm not going to write what the standard basis is again for R2. It's just 1, 0, and 0, 1, right? Those columns of the 2 by 2 identity matrix. All right. So what's the value of t at 1, 0? This is equal to. Well, again, I'm replacing a with 1, and b with 0. So the first component 0, second component 1. All right, so there's going to be the first column of the standard matrix. I'll just write first column. All right, that'll be the first column of the standard matrix. And then and then the second standard basis vector for R2 is 0, 1. All right, so I'm replacing A with 0 and B with 1. Okay, you see how if I replace B with 1, the output would have negative 1 up top and then 0 on the bottom. And here's the second column. All right, so the standard matrix for T is this 2 by 2 matrix, right? There's 2 columns and each one has 2 components, so 2 by 2. 0, 1 for the first column and negative 1, 0 for the second column, and there you go. All right. If you were just asked for the standard matrix, that's it. But now also that I found this standard matrix, we can now write this too. We can say that the image of AB, T of AB here, is equal to the standard matrix, right? 0, 1 for the first column, negative 1, 0 for the second column, multiplied by the input vector, multiplied by that vector AB. And double check, is this actually equal to what they said up there? And yes, it is. Right? You'd have negative b for the first row first column, and you'd have a plus 0 or just a for the second row first column. It works. Right? All right, so if you wanted some outputs, what's the value of t at 2, 5, replace a with 2 and b with 5 here, you could multiply this matrix by the vector 2, 5, or just, this is a really simple one again, it would just be negative 5, 2, wouldn't it? And then one more time here, again, between Euclidean spaces, it's much easier to see, but you see the standard matrix here. See how the first column is just the coefficients of A down this output? You know, there's no A here, 1A there, 0, 1. The second column of the standard matrix is just the coefficients of the second variable, B, which is negative 1B here, no B here, negative 1, 0, negative 1, 0. All right, so if you really want to quickly make the standard matrix, you can do that, especially when you're looking at vector space transformations between Euclidean vector spaces. But keep in mind, though, that you can still find this matrix. You can find a matrix for a transformation, a linear transformation, by plugging in basis vectors from the domain, right, and seeing what the resultant images are, and use those images as the columns of the standard matrix, or the matrix representation for the transformation. Alrighty. Alright, so just those few examples, and hopefully not too crazy, not too difficult. And I hope you enjoy and have fun practicing problems of this nature, and thank you very much for watching.